All right, so welcome to the second day of Midwest.io. A lot of good talks the first day, so pretty excited to be the first talk after the keynote this morning. So let's jump in. So I want everyone for just a moment to imagine that you're joining a new development team, and this new development team, it uses the technologies of your choice, your favorite languages, your favorite source control, your testing frameworks. I mean, you're really excited about joining this development group because it really aligns with the way that you would approach problems. So you're there, you're ready to jump in on your first project as part of this development team. You have your code up, everything's ready to go. You hear that the initial project for the development effort is some sort of resource, some sort of material acquisition project. You don't really, not the most glamorous thing, but it's a good team. It's a good technology base, so you're ready to jump in. You just need to get some details on what is this system that you're supposed to build. So finally that details come through, and you're shown this. So this is the integrated, I actually have to read this, Integrated Defense Acquisition and Logistics Lifecycle Management Framework. This is real. So actually, if everyone could just take a minute to understand this, I'm going to grab I'm going to grab a drink of water here. But yeah, so I mean, I went out and I found the most complicated one that I could find for depictions of systems on a single slide, but this is not without competition out there. I mean, this comes from the Department of Defense, but a lot of big organizations, government in the industry, they see things like this. So how do we approach a problem that faces this level of depth, this level of complexity? And the first thing is, obviously, the users of this system don't try to think of everything at once. These requirements will come in piecemeal. These specifications, if you can call them specifications, will come in one at a time. They're plugged in together. And since our users don't have to think about putting it all, wiring everything up, they have that luxury. So I think the first step that we need to do is think about, hey, how can we break this down into pieces? There's no way that anyone can fit that huge diagram in their head. So how can we start breaking it down to pieces so we can actually build the system? So naturally, our first step is let's look at the tools that we have. What's on our tool shelf? What's in our toolbox to start attacking these problems? So we look at a functional decomposition approach. If you're on the functional side of things, or what sort of object models for object-oriented approach, how will we tackle this problem? And either way, it breaks down to things like where we have a couple of pieces of input, and I'm narrowing down to a very small piece of that picture. And then we'll have some sort of transformations that take that input, create some new piece of knowledge that exists in our system. And then we pile on top of that, where we combine others in a different way to produce some new piece of knowledge, and then bring it together. And you can see these systems just wired up into emerging these new outcomes. And this applies to a lot of industries. So whether it could be, say, travel expenses for getting an expense report for billing a client. It could be some sort of demographics. Let's put together our order history and demographics, and what kind of sales package should we put together? Could be in the healthcare space, where we have our diagnosis, our history, and we're trying to create a plan of care. And this sort of pattern of taking these inputs and composing them together to create a new unit of knowledge, it really applies pretty broadly in a lot of spaces. So the pattern works, but the problem is we have to wire all of these things together. I mean, it looks pretty clean like this. It doesn't look quite as clean when we start connecting the dots. It starts looking like this. And then, of course, things change. New needs emerge. How we wire these things together changes. What sort of inputs each one of them change. So if we add a new input to the system, suddenly we've got to wire that together as well. Every place where some function was invoked, if we change what it needs to do its computation, we have to make sure that we update every place where that's called as well. So we take this approach and now try and do this with that image that we looked at early on. Try doing this with a system with thousands of requirements from many different sources, from many different domain experts. And it just doesn't end well. So we have this challenge in that individually these pieces are manageable, but the explicit wiring of everything together of these systems is complex and it's error-prone, and it's a lot of work in order just to do the plumbing between these units of logic. So, being an engineer, I really like to make the computer do as much work as possible for me. So we need to ask your questions. If there is an unambiguous relationship between these units of logic, why are we wiring them by hand? Is there a way that we can wire these units automatically? So if we look at this example, how would we express this? How might we express these individual units in ways that we could wire them together? Well, one way to approach it is to take every unit of logic that we're working with and just think of what are its inputs. It has a type. If in languages, that define whatever the typing system of your language is, it might have some constraints on what the inputs are. And then when all those inputs are satisfied, it invokes some action. And that action could be contributing a new piece of knowledge back that's then consumed by something downstream, or it could be a side effect, or it could just simply be placing something in the memory that we can query, that we can ask things about it. So when we get down to this approach, this explicit wiring of things together, and this starts to look a lot like a rule engine. And after all, it's just, if this, then that. If these inputs are true, and do this sort of thing. And this is great. And in some domains, treating this as a simple rules engine, there's a lot of them that exist, both in open source and commercial projects. If you can express it in terms of this domain, in terms of a rule engine, you're in good shape. And rule engines work great, if then that, until it's not. And I don't know if you've ever seen, I'm working in the JVM world, if you've ever seen the most popular rules engine in Java is Drools. If you've ever seen rules like this, where it's like my rule, it's a pile of code and another pile of code. So great, what have we really bought ourselves here, other than the fact that Java doesn't have a great way to express this at all? And really, what this becomes is if it's when this, then that, and it's just Java code embedded on each side, all we're doing is basically creating a different control structure. It's just that Java doesn't have a way to express that control structure very well, and frankly, it doesn't have great expressive ways to create, the pile of Java code on either the left-hand side, the when, or on the right-hand side of the rule, the then. So, how else can we approach this problem? Let's try and make it a control structure, but a first-class one, something that's real, that participates as a first-class entity with the full expressiveness of a host programming language. So it's no longer some add-on of where I'm writing code in a DRL file instead of a .java file. What if we make it a first part of our development process with all the advantages of making it a first part of our development process? So it turns out that this isn't necessarily a new idea. There's a few things out there that do it. Newells is basically a JavaScript version of Drools. It was actually written largely here in Kansas City by folks at C2FO. There's a Ruby, something called Wongi in Ruby. It's out there. It seems to have momentum. And then the last one that we're going to talk about today is the project in Clojure called Clara. So we're going to emphasize that one a little bit. Only partially, mostly because that's the one I wrote. So the next question is so why Clojure? Why is Clojure a good tool to tackle this kind of problem? And there's a couple reasons. One is that Clojure has a really strong opinionated core principles in terms of how the state space of systems can be managed. It's very opinionated about things like immutability. And so there's a strong basis there. The other piece is that it's, as to refer to Guy Steele, you can grow the language by adding new control structures, by adding new constructs, and it's really with macros. Now, if you haven't used a Lisp or haven't written a lot of code extensively, macros can seem like this really daunting thing. But really, all macros are, at their core, it's a really simple idea. All it is it's just a function that's run at compile time and takes a set of code, an expression at compile time, and transforms it into a different expression that can be executed at runtime. That's all it is. It's a function that transforms code at compile time. But this alone is really a powerful construct. Entirely new features have been added to Clojure as libraries rather than part of the core language. And these features include things like Prolog-style constraint programming in terms of the core logic library in Clojure. There's also Go-style parallelism is added as a library in Clojure by using macros. It's an incredibly powerful construct, and frankly, it's amazing what those things can do. I don't know of another language that can have that sort of expressiveness added as a library that can be grown. So our use of macros here in this is important in the domain of rules and the domain of adding it, because what we're going to do is we're going to add rules functionality basically as a library into Clojure. And it works a little bit like this. So here's some valid code using the Clara. And it's just simple. It's like if it's a work order, it's high priority, we'll report it. And then we might have something else that inserts some derived fact from it. Now, the left-hand side is just a type, and then it's just a Clojure expression to match things that satisfy that. And then the right of the arrow is just another Clojure expression that can insert new knowledge into the working memory, or it can even have side effects when that makes sense. And this is just Clojure code. It's just a new control structure that's offered in Clojure to do it. And what happens is that when we compile it, or when you start up the JVM, before you run anything to it, since we're often just JIT compiling these, it will take this code and then we'll run it through a transformation and to create a more efficient structure in which commonality between these two rules are combined. What happens when we insert new knowledge into our system, into our working memory, we'll just go find all the instances in which that's needed. We'll match those input types for those functions that shown earlier, and that'll flow through the system and apply the side effects. And it can do so pretty efficiently. I mean, this is just, if you're familiar with rules engines, we just implement a variant of the ready algorithm, where facts enter in the system and flows down. We do a few things that are a little different than ready in Clara. We have a lot of good set operations to make things a little more efficient. But this is the key of it. So, and by the way, I blew my animation budget for this talk on this transition, so kind of want to do it again. But and it's a good, and since I did blow my animation budget on that transition, it's a good thing that I need to step out of Keynote for a second here. Well, let's look at the system itself for a little bit. So then this is the most daring part of the talk, is switching over to demo mode. So we'll see if this goes. Hey, all right. All right, so let's look at some of the actual code here. So some of this is just some setup stuff. We're defining some records that are used in the working memory for the session. As a side note, another nice thing that we can do by growing the language is these record structures are actually defined by a nice library called Prismatic Schema. It's actually not part of the core language, but allows us to define schema for our structures or for our inputs and outputs of functions to give us some of the advantages of a statically typed language. So you can actually see what these things are rather than just names without any constraints. So we'll set up some records here, and I'll just flip through the rules here, and then we'll start playing with this stuff. And so you can see some simple rules, like in this case, if there's no line items, then the order won't be validated because there's a validation order. We can also call functions. So in this case, we might need approval required if the date is too early. So nothing spectacular, but really the important thing is that there's so much of the code in the world just is this sort of thing. We love going to developers conferences and we love looking at some of the really cool, the emerging stuff, the bleeding edge stuff, but there's so much of the world's logic is just the plumbing, just the wiring of this sort of thing. And really, I think that we have an opportunity to make that a lot easier to work with. So a couple other example rules that we'll use below. So let's jump in. So the first thing that we'll go and run is we'll create our session, a session object here, and it's pretty simple. We'll just create a session given our namespace here, insert a few facts, and fire the rules. And now we can query that. In the first query, there's no validation errors in that, but I can query this again and see, hey, we need approval for these reasons. that's pretty much the simplest use case. One thing that you'll see in a few times this demo, if you're not familiar with Clojure, is this. I mean, this is the threading macro. It's one of the really nice features of it. There's a couple variants of it for different needs, is that you can take the input of, or take the return value of one function and just thread it as the input to following functions. So all this is doing is creating a session, then taking that session, inserting these items, and then firing our rules on it. So see that a few times. The other thing that we find pretty important in the Clojure community, has a lot of value, is it's very opinionated about everything being immutable. And this helps make things really easy to reason about. So in this case, I'll create some session, S1. I'll insert a few facts into it and fire the rules. And in this case, there's nothing that needs approval there. But if I take this same session, S1, and I insert something new that makes something trigger, then I can refire that. And so we have something that matches there, a rule triggered. But if I go back to the original one, that original session is unchanged. Because even though I'm threading this working memory into some new knowledge is being added to it, it's really not adding it to the existing one. It's creating a new working memory and adding items to it. Clojure provides some really great data structures to do that. It shares a tremendous amount of state. I'm not copying the entire working memory to a new one and just adding that. I'm just basically doing a very small update to that. But this sort of ability gives us a lot of leverage. So for instance, I can speculatively insert things into a working memory. And if a failure occurs, or I hit some state where, this approval is required, I'm going to cancel that, I can just hold on to the reference of my previous working memory and just reuse that. It also allows me to participate in a transactional manner. So if I'm storing stuff to a database, I can insert things into a working memory at the same time. My transactional fails, then I just go back to my previous version. This sort of strong basis of immutability, I think, really makes a lot of problems a lot simpler and a lot easier to work with. And I think that is important if you're designing something that adds a new control structure to a language, like we're attempting to do with Clara here, that you participate as a first-class citizen in that language. And that's what we've done. Another important pattern that we can do on top of this is that if we have some reference data, we can actually create a session that just has that reference data, and then you can just reuse that. I don't need to copy it. So I have some reference data here that says, hey, delivery of kryptonite to the Fortress of Solitude, probably not a good idea. And so there's a couple items there. So then at runtime, I can just store that session essentially as a global variable because it's immutable. I can share it across threads. It's entirely safe. Then if I want to actually execute some logic, I can take that immutable variable, insert some new logic, and then execute it. And so you can see, hey, approval is required because it met that restriction. And this allows us to compose. Somebody else can build reference data. You can pass your working memories around. It really can become a first-class item as we develop code. And of course, you can invoke it from arbitrary Clojure code and invoke arbitrary Clojure functions from it. So, and this is just that our original reference session is unmodified, so there's nothing matched there. All right. So we showed some examples. And I think that there's some interesting things that we can build on top of this. One of the things that we can do is that as part of this transformation process, as we declare rules and as we transform them, everything that we create is actually a data structure itself. So if I look at this date too early rule that we saw earlier, this is just a data structure. All I did is just pretty printed. It has the documentation, its name, has the left-hand side, tells you what types it matches, the constraints, and then the right-hand side, which is just the code that activates. Do something similar for the other one, actually. Oops. So if we look at this, similar thing. You can see the left-hand side, we accumulate a sum of the price, from line items, and the constraint is if total is greater than 1,000. So we can see inside this code, and then the actual reading network itself is also data. This is going to just scroll off the screen, but so as we transform that, all of our transformations are a data structure itself that can be inspected. So the more interesting thing, as opposed to just looking at this in text, is that since everything is data, all of our code structures are data, we can actually leverage that to do things. So in this case, let's look at a visualization of the reading network. Go over here. So this is just a graph viz, and since I have a number of disjunct rules, this isn't a fully connected network, but you can see sort of the logic flow. So line items flows through that, and this is more of an internal depiction of it, of how the data would flow through our reading network. So if you're familiar with rules engines, this probably has a little bit more meaning to you. You can see how items are joined. But I think that's more interesting than showing a projection of the reading network is actually showing projections of our logic, showing what does our logic look like. So in this one, we can see a more logical depiction. So rather than showing the reading network, we can say, hey, what's everything needed for approval required? And I know this scrolls off the screen a little bit. You can see the different rules that, hey, if the work order is within 2 dates, that flows into needing approval. Or if these constraints about a restricted item apply, that needs approval. And you can you can compose these together and start visualizing our logic. Now, what I think is interesting is that if we look at this, each one of these rules is written independently, but we're creating a projection that assembles all of the logic together to allow us to view it holistically. And we'll talk a little bit more of that in a minute. And since this is just data structures, again, we can do things like we can look at only the subset that we're interested in. So here we'll get our rules, we'll get our productions, we'll filter those productions by whether they insert this validation error, and then we can look at the logic for only things that insert validation error. So essentially what we're doing here, that one's just one item, we'll do something a little more. This one, whether it inserts or uses the approval required fact in our working memory. So here we're looking at the subset of our rules that deal with whether approval was required. And this is kind of neat, because if you look at the visualization here, which we looked at before, but if you look at this code, essentially what we're doing is we're querying our logic. We're querying our logic for what creates approval required, where do we use approval required, and then we can take that query and render it, and this simple graph is. This is a hack that I did, but you can imagine more sophisticated ways that we can actually query and explore logic. And this is possible because everything is data underneath. We can also create rules. So in this simple example, it's like, since it's just a data structure, you can imagine an editor or some other tool creating rules in this data structure, and then creating sessions on the fly. Another challenge that we have is explaining the behavior of our systems. So in this case, so if you think back to that hugely complex diagram, when some output pops out the end of a system that implements that, it's not always clear why did that output arrive, because there's so many variables that input it. So a user, the system may be correct, the system may be working fine, but a user sees an output that is difficult to understand, and they're going, what's going on here? This can't be right. But what if we could explain to the user why an outcome was arrived at? I'll make this a little smaller so it reads. But so in this case, here's an explanation of why the restricted item is fired. So it executed this side of the rule because there was a work order for that location, and there was with a line item of kryptonite, and that's a restricted item at that location. So this is a fairly simple example, but you can start composing these on top of each other, even to the point where we could look at any execution and say, why did this happen? And we can trace back to all of the pieces of information that led to that. And I think that there's a lot of use cases in which a lot of support calls could have been avoided in a lot of industries if there was some way that I could, every time I see some sort of derived outcome from some complex set of processing logic, if I could click on that and say, why is this there? And sometimes it's supposed to be there, but if it's a legitimate bug, then our signal-to-noise ratio for actual bugs entering the system becomes a lot better. And so this is just another example deeper in that space. So we'll kick back to the keynote here for a little bit. Oops. So these show some of the leverage that we can get, some of the tools that we can have, but more deeply, collaboration with our users is our biggest challenge. And we have this gap, between what our users actually want and what the system does. And what's interesting is that agile development has probably been one of the best steps forward in helping close this gap. And it's because we've created this feedback loop in our system. We can build pieces of the system. Our users can review that. We can write unit tests against it to make sure it's correct. We can get that feedback, and we can continue to get that continuously improving self-correcting process. And this is great. This is quite possibly the biggest step forward in engineering practices, maybe ever since the rise of higher level languages. So Agile is great. And you can see, just look how happy these people are. So it's great, but then we see this, right? And it's like, make this agile. I mean, how do we approach this? I dare you. How do you take this and apply an agile process? And I think that so much of the challenge here is that deep complexity in the system hinders that feedback, that self-correcting feedback loop that helps us improve our code. Agile works well when a user can explore the subset of functionality that they need. When you do an iteration, here's some new functionality, if they can use that functionality. But if that functionality is buried deep in some crazy edge case that you have to go through a combinatorial explosion of items to get, you're not getting that feedback loop. So there are classes of problems, and I'm a huge proponent of agile development, but there are classes of problems in which an agile approach is not sufficient. And we can do things like unit tests. I mean, again, unit tests, excellent, huge step forward, but all the unit tests are really testing the developer's understanding of the systems that we're building. It's not testing, it's not actually validating, hey, is this doing what the user wants? It's testing whether it's doing what the developer thinks the user wants. It's an important step, but they're not sufficient. We can document our systems, but they're ambiguous. They're subject to interpretation. So again, we're not creating that feedback loop that we would like. So the one place that has an unambiguous specification that really says what our code really does is the code itself. I mean, code is the closest thing to a blueprint that our industry has. But code is too complicated. It's not an artifact that we can share with the user saying, hey, this is right. And our systems are too complicated that we can't have them click through the system and hit every use case. So the question is there a better way that we can work with our users, that we can collaborate it? Now, I couldn't design a house. I couldn't design a building. And frankly, looking at these blueprints, they can be hard to interpret. But what I could do is if I could see a floor plan. Other industries have these ways of creating projections of their design, simplified projections of their design that's accessible to a layperson. I may not understand a blueprint, I certainly couldn't design one, but I can look at a floor plan and get a good idea of what's going on here. And I think that this is our opportunity to, if we structure code as these declarative rules that are closer to the needs of our user, and this applies pretty well in certain domains, and then we create those projections. If we project things onto something like this, or there's a lot of other variants that we can do that, I think we get a little bit closer to creating a floor plan, creating an unambiguous document that can be used, leveraged, understood by a user that's not as deeply technical. Now, I don't know if our floor plan is going to look anything like this. I guarantee it's not going to be just a simple graph viz hack that I did on the side. But we can take a step in this direction by creating these simplified projections of our system. And really what it boils down to is getting leverage from our investments, getting leverage from everything that we're building. If we start by creating a direct expression a more direct expression of our user requirements. So we're declaratively as close as possible saying, hey, this is what I want to do in all these domains. And then we take that direct expression and we take it and put it in the form of rules, and view those rules as code, but there's essentially transformed into data as well, data that we can query so we can ask questions about it. And we can create those into projections of logic. We can start creating explainability. We can explain why did this outcome arrive there. We can query that, and we can build things like floor plans. And floor plans, just, I don't think quite does it justice. I'd love a better metaphor for this. Because floor plans are static, they're two-dimensional, they're pieces of paper. But if we have this ability, if we have this leverage by having our logic mapped to our users' needs in a data structure that we can query and explore in arbitrary ways, then we've created a mechanism, we've created a source of leverage that everyone can tap into and build new ways to explore our business logic and new ways to collaborate with our end users on this business, for our business logic. And I think this is one of the biggest opportunities that we have in terms of raising up rules as a first-class control structure and obtaining that leverage in a language. Clojure is one example, but I think that I think this could be done in a number of expressive languages. So with that, we have some time left for some questions. Yeah.
Looking at those rules, could you also use them to do possible corrections, like if zip code was missing, then fire another rule that looks up a zip code based upon the address?
So the right-hand side of the expressions of those rules, it's an arbitrary closure function. It could invoke an arbitrary lookup function and insert additional information. One of the goals is that a lot of the existing rule engines I think are too constrained, and that, hey, that's great if I meet these use cases, but we want to lift those constraints. We want the full expressiveness of the programming language. So things like a lookup or insertion, that sort of thing would totally make sense. It's a good use case.
So you talked about constraints living in external files and databases. Can these rules also live in external files so that they are more configurable by our end users and they can author their own rules?
So can we put the rules in external files and make them configurable? And since they are a data structure, they could be stored anywhere. Under the covers, we have this nice def rule declarative syntax, friendly for those of us who live in the Clojure world. But it basically is just a data structure. You could store that data structure anywhere. You could in a file, in a database, or something like that, so they could be edited. I think that there's an interesting. I think that's an interesting question, though, because when you start doing that, then you lose the benefits of a lot of the rest of the software development lifecycle, so you're not running through tests or that sort of thing. I think a lot of times when rules are externalized like that, it's because it's too hard to deploy code updates. But I think that I would rather solve that problem by making it much easier just to push out updates. There was a talk from some folks at Huddle yesterday that showed code updates many, many times a day. So I would almost, I think that putting rules in external files is fine for some use cases, but I think that the end game is to basically treat rules as code and be able to treat them as code updates and just be able to do that a lot more quickly. But yeah, it's a good question. All right, any other questions? Cool. All right, well, thanks a lot. I appreciate it.